Here's part one of my talk. It's about singularities in surface theory. So in this part, what I'm going to do is first show you some visual examples of the typical types of singularities that we get in surface theory, and something about how they arise, and then just a little bit about how you can analyze these singularities. So if you already know about singularities in surface theory, you can probably skip this part and go on to the part about spherical surfaces. So let's look at some examples of what I call integrable surfaces and their singularities. So by singularity of a surface, what I mean is just a point where the rank, so we have the surface is an immersion, a parameterized surface. It could be from any two-dimensional manifold to three-dimensional manifold, and it's points where the rank of this map is less than 2, points that are not regular. So this, if it was a surface in R3, this would be the condition. The cross product of the partial derivatives were 0. And here's two fairly representative examples of singularities. This one is what's called a cuspidal edge. It just looks like a folded piece of paper. And this one is called a cross cap. It's just at one point. So the difference between these two, one of the differences between these two singularities is that here you have a well-defined normal, which will be important later, along the curve, but here you do not. So stability of singularities means a singularity is stable if you deform the surface a little bit. If nearby surfaces still have this type of singularity, then it's a stable singularity. Otherwise it's unstable. There's an old theorem that says that if you look at generic maps from R2 into R3, then the only stable singularity is this cross cap. But if you restrict to a specific class of surfaces, so for example constant curvature surfaces, you can get other types of singularities that are still stable. So a swallowtail will be stable in that class of surface, and a cone point will not be stable. What you can show is that the stable singularities for constant Gauss curvature surfaces are the cuspidal edge, it looks like the one on the left, and the swallowtail, which looks like the one on the right. So this is the swallowtail singularity is just at that point there. So everywhere else around there you have a cuspidal edge, and the curve that makes that cuspidal edge has a cusp point in the image just there. So let's talk about classes of surfaces which have natural singularities. You probably know about tangent developables. If you take a space curve, a curve in three-dimensional space, and you look at the envelope of tangent lines to this curve, this sweeps out a surface which on a neighborhood of that curve, not including the curve, is regular, and it's singular just along that curve. And this is you can think of this as a typical zero curvature surface in R3. Another natural example is parallel surfaces. Here I'm giving the example of parallel curves to a curve. So here I have a curve which is regular, then I move a fixed distance in the normal direction to the curve. I get another regular curve. If I keep doing that, eventually I get to a point where it's not regular, and if I keep going, then I get two cusp points on the on the curves further on. Get a similar situation for surfaces. So this is a parallel surface to a regular surface, and here at some point we developed this cuspidal edge singularity. Here's another example. Here we're developing a swallowtail singularity in our parallel surface. You can kind of see from that animation that swallowtails are also generic singularities for parallel surfaces, or you might guess that, because that once the swallowtail appeared, you kept getting swallowtails in subsequent surfaces. Okay, so constant positive Gauss curvature surfaces are an example of parallel surfaces. So here are some images of constant positive Gauss curvature surfaces, which are made using harmonic maps, which I'll talk about later. But as I said, you can realize them as parallel surfaces to constant mean curvature surfaces. If you have a CMC 1/2 surface, and you write down the parallel surface of distance 1 to that surface, then you can check that this surface F will have constant Gauss curvature 1. And if you look at this formula here, for the cross products, you can see that wherever the CMC surface has 0 curvature, any point where the CMC surface has 0 curvature, the corresponding CGC surface will have a singularity, because the cross product will be 0. Here's an example. In the middle you have the constant Gauss curvature surface, and since there are 2 choices of normal, we can get 2 parallel CMC surfaces to this. So another thing we talk about in singularity theory is bifurcations, which is transitions between different types of generic singularities. So this is an example for constant positive curvature surfaces. Here we have 2 cuspidal edges, and over here we have 2 swallowtails, and the point just in the middle where you go from this to this is called a cuspidal beaks bifurcation. Here's a realization of this bifurcation as families of constant positive Gauss curvature surfaces. So besides parallel surfaces, there's another way that you can get CGC surfaces or constant positive curvature surfaces, and that is through harmonic maps into S2. If you take a harmonic map from complex from C into S2, it satisfies this equation, and then you can easily check that this equation is equivalent to the integrability for this pair of PDEs. So you will be able to solve these PDEs if and only if this equation for n is is valid. So given a harmonic map into S2, you can solve this equation, and then you can just check that this if it's a surface, if this map is regular, then its Gauss curvature is 1. And conversely, if you have a constant positive Gauss curvature surface, you can check that its Gauss map is harmonic. So if you look at this for a little bit, you can also see that F is regular if and only if n is regular in this case, but the singularities are different types for these 2 surfaces. So that was an example of what we call an integrable surface. So integrable surfaces are surfaces associated to integrable PDEs, like harmonic maps, soliton equations, etc. I'll just mention a few examples because the maximal surfaces in the Heisenberg group that we talk about later is just one example. So one type of example, you can think of this as a type of example, is constant mean curvature surfaces and Willmore surfaces. And these have the property that they don't have, in R3, they don't have any singularities except for what's called branch points. So these isolated singularities where the surface behaves like z squared or z cubed, etc. But I want to point out that if you change the target space, so if you use a Lorentz space, for example, and look at CMC surfaces in this space, then you get other types of singularities, not isolated singularities, in addition to branch points. Here's an example of a CMC surface in Lorentz space, which is obtained by solving an integrable PDE. So you start, you solve this PDE starting at this central point here where it's regular, and you keep solving it, and eventually the surface develops singularities of two types. One type where it blows up. You can see this in this animation. The surface blows up, and then it comes back in, and then you also get finite singularities here, like these swallowtails and cuspidal edges that you can see here. Okay, so another type, typical type of integrable surface is constant Gauss curvature surfaces, which I've already mentioned a little bit before. And what we can say about those is that there are no complete constant Gauss curvature surfaces with k less than 0. The only complete ones with k equals 0 are cylinders, and there are no complete ones with positive Gauss curvature other than the sphere. So these are a natural surface class which has singularities. Here are some examples which are constructed using the theory of harmonic maps, Lorentzian harmonic maps. I won't talk about the theory of these. I just want to give just some examples about what they look like here, and how we can try to visualize the singularities of these. So in singularity theory, since these singularities are a very sort of obvious landmark of surfaces, we try to classify the generic ones that appear in a given class of surfaces. I'll just say a little bit about that now. So how do you analyze singularities? So I'm only going to talk about singularities of surfaces in three-dimensional spaces. So what you do is, first you characterize the germs of local solutions within the surface class, which you can do. Then, of course, there is a singularity at a point P. A singularity at a point P is a germ where the rank of df is less than 2. And the level of genericity is the codimension in the space of k-jets. This is again within the relevant surface class. And what we want to do is classify them up to A equivalents. So that means that F is equivalent to another germ if you can find these local diffeomorphisms of the two spaces that take one germ to the other germ. So for example, if you look at these pictures here, these are constant Gauss curvature surfaces. You can see singularities that look like swallowtails on these, here, 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 and here. And if you wanted to show that these are swallowtails, according to the theory, you would have to find these local diffeomorphisms between those and this standard swallowtail here. But of course, you don't want to do that in general. So there is some recognition criteria that have been developed for various types of surfaces that we can use instead. I'll just give a hint about that, about how that's done. So we're talking about the class of surfaces which have a well-defined normal, even if the surface is not regular, and that's called a frontal. So if you have a map from a two-dimensional space into three-dimensional space, F, and another map N, which is into the unit sphere bundle in the tangent bundle to M, such that N is orthogonal everywhere to dF, then you can think of N as a normal to F, even if the surface is F is not a surface. And we've seen an example like this already, where if you have a harmonic, for example, a harmonic map into S2, you solve this equation, you get this map F, and if you just look at this equation, you can see that F is orthogonal to N, because this product is orthogonal to N, and so is this. And these are the potentially two tangent directions to F. So this is the frontal and therefore if we have a theory of singularities of frontals, we could use this to study the singularities here. The type of frontals where there's so far a good theory of singularities is wavefronts. This is I guess you could say this is a generic frontal, because a wavefront is it's a frontal where this map Fn is regular at every point. And it's easy to check that this is the same as saying that locally this is F is a parallel to a regular surface G. So it's been known for a while that the generic singularities of wavefronts are the swallowtail and cuspidal edge, and the codimension 1 singularities are these, I won't name them, singularities that you see here. So how about recognition of singularities? With wavefronts, the singular set is generically a curve. Let's call it sigma. And the kernel of df generically defines a vector field along the curve. And you can use these two pieces of information to identify the two generic singularities. So you have a cuspidal edge at a point where sigma is regular and eta is transverse. This kernel of df is transverse to sigma, and you have a swallowtail if sigma is regular and the kernel of df is parallel to first order to sigma. So there are more criteria like this for the other types of singularities that I showed you on the previous slide, but I won't mention them right now. So that's everything I wanted to say here about theory of singularities. If you pause this slide, you can have a look at these references. There are two books here, the one by Arnold about singularities, and this more recent book by Izumiya and others. And you can read about a recent survey by Ishikawa about the recognition problem for frontals, which is, I believe, still an open area. And here you can read about the singularities of the generic singularities of fronts in, for example, this paper here. Okay, so the next part of my talk will be about spherical surfaces.